Picture a 500-person engineering team literally losing thousands of hours this quarter, and not to poorly written code, but to configuration drift, the silent, compounding tax of a heterogeneous operating system fleet. We're not here to discuss the basics of containerization today. We already know that. We are here to architect absolute environmental parity. Exactly. This explainer serves as your architectural blueprint to completely eliminate that fragmented reality. Because when an enterprise scales rapidly, that old works on my machine excuse across diverse Windows, Mac, and Linux environments, it becomes an absolutely unacceptable vulnerability. Our fundamental goal here is to form a zero-drift core, standardizing these diverse environments so the underlying runtime is mathematically identical everywhere. Right, and that identical execution, achieving byte-for-byte parity, is the ultimate architectural objective. At the OS level, we're manipulating Linux namespaces for isolation and control groups, or C groups, for resource management, all of them sharing a single underlying Linux kernel. But this architecture introduces a silent threat, a root privilege trap that can easily lead to catastrophic host starvation or complete node compromise. It's a severe vulnerability, and we are going to deeply dissect it when we analyze the Linux native engine a bit later on. Before we can solve that looming security flaw, we first need to address the fundamental split in our deployment strategies. So, Section 1, Engine versus Desktop, and our architectural divergence. Let's use this as a fresher and mid-level calibration checkpoint. For those of you transitioning into deep infrastructure, you really have to weigh these strict architectural trade-offs. Docker Engine, well, that's raw, unmanaged daemon execution running natively on Linux. Docker Desktop, on the other hand, is a commercial product. It completely abstracts the complex hypervisor networking required on non-Linux machines, wrapping the engine, a GUI, Kubernetes, and a managed VM all into one comprehensive package. Scaling cloud production requires the raw namespaces of the engine, but scaling local developer experience, that requires the abstraction of desktop. For our senior-level calibration checkpoint, the virtualization tax of running that managed VM is definitely one consideration. But enterprise compliance is another beast entirely. For corporate fleets exceeding 250 employees or 10 million in revenue, paid desktop subscriptions are a strict legal mandate. You just can't rely on ad hoc manual downloads across a team of that size. Scaling this legally necessitates centralized license management and automated mobile device management, or MDM, deployment. Let's dive into the specific workstation environments. Moving on to Section 2, Windows 11 and the WSL2 paradigm shift. We really must evaluate the strict trade-offs of legacy architecture here. We've got to bypass the old Hyper-V tollgate. The overhead is simply too high for modern microservice development. Enforcing WSL2 integration, that's the Windows subsystem for Linux 2, provides a true Microsoft-built Linux kernel. This yields near-native file I/O performance and drastically faster cold starts. The trade-off is incredibly clear. Drop the heavy legacy emulation and embrace the lightweight utility VM. Which brings us to another fresher checkpoint. What exactly is WSL2? And why does Docker strictly require it on Windows NT architectures? Well, the answer is foundational. Linux containers fundamentally rely on kernel features, specifically the namespaces and C groups we discussed earlier, that simply do not exist natively in the Windows kernel. Without the true Linux kernel provided by WSL2, the container engine just cannot execute. So the crucial point is how we enforce this standardization silently at scale. We utilize a silent PowerShell deployment strategy. Step 1, enable the WSL2 feature natively. Step 2, execute the desktop installer by passing the quiet and accept license flags. Zero human intervention is required there. But step 3, this is where enterprise architects earn their keep. Enforcing a .wsl config file globally to hard limit memory to 8 GB and 4 processors. This critical configuration absolutely prevents the host starvation we warned about earlier. With the Windows fleet securely locked down, let's pivot our architectural sync over to the Apple ecosystem in Section 3, macOS architecture and silicon translation. The scaling challenge here is the execution boundary, specifically navigating the silicon translation between ARM64 Apple Silicon and traditional AMD 64 architectures. If you deploy an image built natively on an M-series Mac directly to a standard cloud server, it will crash, period. You incur a massive Rosetta 2 translation penalty otherwise. The absolute necessity here to bridge this gap safely is using Docker BuildX to compile multi-arch manifests. That ensures native execution in production without any of those emulation penalties. Which brings us squarely to the raw production environment itself. Section 4, Linux native execution and the security posture. It is finally time to close that open security loop we established earlier. Let's meticulously break down our deployment methodology here. When deploying the Linux engine, imperative bash scripts fail unpredictably at scale. The naive approach, piping a remote script directly to sudo bash, is disastrous and completely non-idempotent. The standard approach of manual GPG pinning, well, it's stable, sure, but wildly inefficient across thousands of nodes. True enterprise standardization demands the enterprise approach, a declarative Ansible playbook that provides zero-touch, immutable state enforcement. And to secure those Linux nodes, and for our mid-level checkpoint, consider the blast radius of a compromised container. If the traditional daemon binds to a socket owned by root, and an attacker breaches that daemon socket, they own the entire host file system. Game over. By isolating environments and utilizing user namespaces to deploy in rootless mode, we aggressively mitigate this root-level socket breach. Because even if an attacker escapes the rootless container, they fundamentally lack administrative privileges on the host kernel. Which leads us directly into our senior checkpoint, really the ultimate test of an architect's systems thinking. Given everything we've discussed so far about divergence and security, how do you immutably automate Docker engine installation across 500 Linux nodes simultaneously? You achieve this by completely treating infrastructure as code. Step 1, programmatically ensure the official repository and GPG keys are present. Step 2, install the core engine via apt state enforcement. And Step 3, ensure the systemd service is perpetually started. You see, configuration management tools like Ansible don't just install things. They continuously detect and correct configuration drift automatically, enforcing state securely right back to your Git baseline. We've analyzed the individual operating systems. Now for Section 5, Enterprise Fleet Standardization. Let's pull all these heterogeneous OS threads together into one unified, standardized enterprise ecosystem. This unification builds a highly predictable reality. We're transitioning entirely away from live, fragile configuration, moving toward predictable atomic Docker images. There is a profound architectural synergy here. Ansible flawlessly configures the raw server foundation, while Docker handles the isolated atomic application runtime. Never patched live, only replaced. But even with perfect foundational deployments, resource exhaustion remains a critical threat. Running containers without constraints essentially invites the out-of-memory, or OM, killer right into your production environment. By hard-coding memory limits and CPU shares directly into our run commands and orchestration manifests, we leverage C-group resource control to ensure high-density, absolutely unbreachable resource distribution. To further that control, we absolutely must debunk the root myth entirely. Enterprise containers rarely need true root privileges. By aggressively dropping all kernel capabilities by default and then selectively adding back only what is functionally necessary, like net_bind service for a standard web server, we establish a mathematically verifiable zero-trust environment. And that zero-trust posture absolutely must extend upward to the supply chain. Pulling unverified images from public registries exposes the internal network to malware. Simple as that. Securing this pipeline requires cryptographic signature verification via Docker Content Trust. By enforcing trust pinning within the daemon's execution path and migrating strictly to hardened minimal base images, we algorithmically eliminate untrusted code blocks before execution even happens. To orchestrate these trusted containers efficiently, we map our multi-container topology declaratively. The Compose specification is a completely cloud-agnostic standard. It elegantly and seamlessly translates the local development environment running on that standardized WSL2 or macOS desktop we structured earlier directly into cloud-native production deployments. So, we arrive at our final architect-level checkpoint, the complete, standardized enterprise deployment blueprint capable of supporting 1,000 engineers. To summarize our entire matrix, we deploy the developer experience silently via MDM, we lock down the admin settings.json to enforce private signed registries, and we mandate enhanced container isolation and rootless daemons globally. Ansible provisions the host, Docker dictates the runtime. As you review your own architectural blueprints following this explainer, ask yourself this: will your infrastructure scale immutably, or will configuration drift remain your quietest